Okay, so let's look at some of the details, right? So how we can generate this kind of adversarial attack so that the machine learning model will fail in terms of classification. So here is the original image. We denote this as X0. Okay, so this is the clean image, and the network is able to generate a very good prediction of this is a cat image, right? So this is the classification output, right, of the probability. So for simplicity, right, we look at these three maybe high probability output. The cat is a high probability, right? So this is the correct label. And we are fixed the network parameter, right? So because the only thing here we are change is going to be the input, right? Because we are not going to do anything for the network. So the parameters are fixed. So if we're doing the non-target attack, right? So basically we want the network to output a label, that is not a cat, okay? Anything but cat, okay? So we want to figure out, right, what kind of noise we want to add to this original image, okay? So if we put, adding the noise X, right, we output, go through this network and we generate a label Y, okay? And we want this Y as far away from the ground truth, right, which is the cat, okay? So here, just for simplicity, so this X should be X0 plus X, okay? So that's the noise we adding to the image, and the resulting image have the label of Y, and we want to have this label Y to be as far away as possible from the ground truth, Y hat. So in other words, we want to reduce the confidence or the probability of a cat, right? And maybe bump up some other the confidence of other labels, maybe fish or dog, maybe other classes, okay? Because we are doing non-target attack. Okay, and so we can do this kind of optimization, right? So here we can, again, specify a loss function, and we can using gradient descent to optimize these loss functions so that we are able to generate an image so that the network is able to misclassify, okay? And the loss function here, because we want to make the prediction as far away from the ground truth, right? So we can using the cross entropy as the loss, right? So just like the usual supervised learning, right? We using the cross entropy. Here we can do this here again. We're using the cross entropy as a loss. And here the objective is to maximize, right? These predicted label and the ground truth label, right? So here, because we're doing the minimization, and we can easily do this at a minus sign to the entropy loss here, so that we can still minimize this loss, right? To fit the objective that we want to make these two distributions far away. Okay. So that's the non-targeted attack. But what about we want to do the target attack, right? So in this case, we have a target label, right? We call it Y target. So this could be like a fish class, right? So in this case, we want the prediction, right, Y here to be close to the Y target, but this Y target is not the ground truth Y hat, okay? So if we designate this target as a fish class, right, so we want to increase the probability for this fish class. So in this case, we still want, right, the prediction as far away from the ground truth. So we want to keep this term, okay? But another thing is we want to do the target attack, right? So we want to add another term, right, to minimize the discrepancy between the prediction and the target label, right? So we add an extra cross entropy loss for this target label. So then that formulate the objective function if we want to do the target attack. Okay. But this is enough for the adversarial attack. So remember when we, in the introduction, right? So when we do this adversarial attack, we don't want to introduce a noise that is noticeable, right? Then, it can be easily perceived, right? Then we can notice this may be a tempered image. So the goal is that we want to add in the noise, or the resulting image will be very close to the original one, right? So the X, which is a tempered image, should be very close to the original image X0, so that we cannot perceive any of the difference. So we have to add in additional constraint, right? So we're using some of the distance measure, right? So this distance measure can be like L2 norm, right? We compute the original image, the L2 distance between the original image and this perturbed image X, and we add a constraint, right? So the distance or difference should be very small, right? To a certain threshold, epsilon, okay? So that's kind of forms the overall objective, right? So we want to misclassify to a specific label, but at the same time, we want to make sure the added noise is small enough, or the perturbed image should be very close to the original one. Okay, so we can talk more about this kind of non-perceivable aspect of this adversarial attack. So for this distance measure, here are two commonly used distance measure. One is the L2 norm, right? So basically we have this perturbed image, and this is the original image, right? So we can compute the L2 norm of these two images, so as the distance measure. And we have another norm which is L infinity. So basically this L infinity is compute the absolute value of the distance, right? In the element wise, right? So for each individual pixel in this image, we compute the absolute value of their distance, and then we take the maximum. Okay, so that's the L infinity measure. So what's the the advantage or maybe disadvantage of these two distance measures, right? Which one we normally pick? So here I provide a simple example, right? So let's say the image is like 2 by 2 pixels, right? So only have 4 pixels indicated by these different colors. One way to adding the noise is that we can change every pixel a little bit, right? So we add a small noise to every pixels, right? So in this case, we generate a perturbed image, right? It may look like this, and because the change we add to the image are very small, right? So so here I just purposely make like they look the same, right? In terms of color and contrast, right? So you are not able to tell the difference. Another way we can do is we can maybe change 1 pixel a lot, right? We adding perturbation to 1 pixel to make the change, right? So here, I don't know if you can notice, the change is add to the pixel indicated by this green color. Okay, so if you look at here, the perturbed image, right? So it become this kind of light green, becomes the dark green. Okay, and let's say if we in this first case, right, we adding maybe 1/2 to every pixel, right? So if we compute the L2 norm, right, what's the difference we get? It's equal to 1, right? Because we add in 1/2, 1/2, 1/2, 1/2. We compute the square. We have a 1/4, 1/4, 1/4, 1/4. We sum them together. We equal to 1, right? And we can do this by adding. If we consider, right, if we just adding the same amount right, we can adding one to this particular pixel, green one. And in this case, we generate the same L2 distance, right? Because we're adding one to this one pixel only, and we have the L2 norm, L2 distance equal to 1. So these two cases are gonna be the same. But if we compute L infinity, right? So in this case, the L infinity is going to be 1/2, right? If we, using this equation here, L infinity, right? So here in this case, we're adding 1/2 to every pixel. So the L infinity is going to be 1/2. But for this particular case, right, we're adding 1 to this green pixel. We have a larger L infinity, right, which is 1. So technically, we can see that this L infinity is going to be a better, measurement or metric, right? Because the goal here is that we want to add in something that is not perceived by human, right? So the L infinity seems to be a better, like a change detector as compared to L2, right? Because in this case, the L infinity is larger, and we are able to detect there's a large change has been made to this image, right? So this may be, tell us, okay, the noise you add to the image may be too strong, right? It is detectable by this L infinity. So maybe you should reduce the noise adding to the image so that it may not be perceivable by human, okay? So that's this case to illustrate maybe L infinity is a better choice to kind of perturb this kind of non-perceivable noise to the original data. Okay. So now let's look at how we can do the optimization, right? So here we have specified the loss function, right? We want to change the input data, right, to make some adjustment of adding some perturbations so that the prediction will be very different from the ground truth. Or if you have a target attack, you want the prediction to be the target label you designated, okay? And at the same time, we want to limit the noise has been adding to the original image, right, bounded by a threshold epsilon here. But first, let's maybe make it more easier, right? We can forget about the noise restriction, right? So let's don't consider that restriction in terms of the noise magnitude you can add to the original image. Let's just look at the loss function here. And remember, in the usual, right, we train this classification to do the image classification, right? We're using the stochastic gradient to optimize the network parameter, right? The weights and the bias term, right? But in the adversarial attack, we are not touch the network parameters, right? Because the goal is that change the input so that the trained classifier will misclassify, right? So in other words, we are going to update the input, not the parameters, okay? But this can be considered the same thing, right? Basically, you can consider this input is additional layer, but you just freeze the network, right? You just change that input so that it will still towards the objective or you specified, right? Maybe minimize this loss function. So here we can, again, using gradient descent to do this kind of optimization, right? If the objective is to minimize this loss function. Here we are starting from the original image, okay? Of course, you can say that why do we, you can ask why do we starting from the original image, right? Why not just a random noise, right? The reason is that, after all, the outcome we want is an image very close to the original input, right? So basically, we just want to add in some small noise. So it's better we just starting from the original image and learn what kind of noise we want to add to the original image. Rather, you starting from random noise and gradually learn a very close image to the original one, but make the classifier to misclassify. Okay, so we start with the original image x0 here, and we can do this for a couple of iterations, right? So here we can again define maybe t iteration or t training epochs, and we can using the gradient descent, right? We compute the gradient in term respect to the pixel values of the input, right? Remember here, we are not updating the model parameter, right? We are only update the input, right? So here, what we want to update is the pixel value, right? And this is the usual stochastic gradient descent, right? So we have the learning rate and we have the gradient, and we update the original input, and we can do this in a couple of iterations. Okay. Okay, now we understand that, right? There's basically the procedure is going to be very similar to you train or optimize a network for classification. Now we consider the condition we want to enforce, right? The difference between the original image and the perturbed image should be very small, right? So we have a threshold epsilon here to act as another constraint. So how do we incorporate this constraint in the optimization? So actually, this is very simple. So what we do is that we can measure the during the training, right? This optimization, this iteration process, we can monitor the difference, right? So we have the original input, and we have the updated input at the tth iteration xt, right? And then we can compute the difference, right? So here, if we consider this L infinity, and we can compute this, L infinity distance for each of the iteration. So, if the distance is small than the threshold, right? We just keep doing this, right? We keep updating this. But if we measure, right, we detect the distance is going to be greater than the threshold epsilon here, then we have to take some, action, right? Because in the condition here that we want to restrict the difference to be less than this threshold, right? So the simple way we can do is, once we have this detect this distance going to be greater, then we have a fixed xt, right? So this fixed xt will have the maximum L infinity, which is the threshold we set here, right? So just an example here, maybe in this iteration, right? So there's one, maybe we're here, okay? And we compute this L infinity, right? Which is greater than the threshold epsilon, right? So this is the boundary we set, right? Remember, this is not L2 distance. It's not a circle, right? It compute the maximum of the absolute value, right? So that's a square, right? So with these half of the lengths as epsilon here. So what do we do is we basically pull this update, right, to this boundary, right? Because you're over this boundary now, and then to satisfy this constraint here, we just pull it back, right, to this boundary. We have this fixed here. Okay, so that's the way we satisfy this condition here. Okay. Okay, so this is the the constraint we impose, right, for the how much of the difference we want to have for the perturbed image. Of course, you can have different constraints for this, maybe in terms of the threshold, or maybe you can have other metric for this, and there's also for different attack approach, maybe you can have different optimization functions, right? So you can add in some additional terms, so that you can formulate a different objective and you can generate a tag to fit that objective function. But here what we discuss is the very basic you can do for the adversarial attack. Okay. Now we look at one very popular approach to do the adversarial attack, that is called the fast grading sign method. Okay, so for this fast grading sign approach, the difference is that we do not do this kind of multiple iterations. So basically, this fast grading sign method is only do this once. Okay, so it's going to be very quickly to generate a perturbation to the original image. So in this case, we only do once, and instead of considering the actual gradient, right? We take the sign function. Okay, so basically the sign function is, if this whatever the value in this parenthesis or the gradient, if it's greater than 0, then we take the +1, right? That's the sign. And otherwise we'll take -1. Okay, so we'll take the negative sign. Okay. So this function basically gives us, either plus or -1. Okay. And typically we set the learning rate equal to epsilon, right? Because this is the maximum we can get, right? So because you're doing just one step, right? So we want to, make sure, right? So in this single step, you are able to achieve the change that is able to alter the prediction of the machine learning model. Okay, so this is the fast grading sign approach to quickly to generate some of the perturbation for adversarial attack. Okay. And we can also do this iterative FGSM, right? So this is a later work based on FGSM. So here, basically, we're not limited to just one single step. Here we can consider multiple steps so that we are able to maybe generate better adversarial noise. So again, so the main component will be the same, right? Still, we are considering the sign of the gradient, but here we can do this for multiple steps. And we still consider the constraint, and if this distance is greater than the threshold, then we'll fix that, right? So we have a fixed output, right, to make sure everything or the output is going to be lie on the boundary. Okay. So in the previous example we presented, right? So when we do the optimization, right? So we know the network parameters. So then we can compute the gradient, or in the fast grading sign approach, we can get the sign of the gradient, right? So in this case, we call this white box attack. So the white box means, right? So the model is available. You have access to the model, right? So the model parameters. So you have access to that. So you can do the optimization. But for some of the applications, right, in particular in real world applications, the machine learning model is not accessible, right? So for example, you have some online machine learning service, right, like the API for you to do image classification, object detection, right? So basically user upload an image to the server, and the server returns the result to the user, right? But the machine learning model is not going to be revealed to the users. You don't know what is their machine learning algorithm they use to generate the result, right? You only get the outcome. Okay. So in this case, does this mean we are safe, right? We are not under the risk of adversarial attack if we don't release the model, right? Unfortunately, the answer is no, because we can also do black box attack, and this can also make the machine learning model to generate false or misclassification. Even the attacker doesn't know anything about the machine learning model. So this is called black box attack. Okay. So definitely this black box attack is a much more challenging setting, right? Because we don't have any knowledge about the network, right? Then in this case, how can we do this kind of optimization, right? To generate the perturbation we want to make the machine learning model to fail to predict the correct class. So there's a couple of ways we can do black box attack, right? So here the network, we consider this is a black box, right? We don't know what's in this network. But if you have the training data of the target network, right? Let's say you know or you have access to the training data, okay? Maybe you have knowledge that this network is trained on ImageNet, right? And because ImageNet is publicly available, right? So that means you can also gain access to their training data, right? Which is ImageNet. So in this case, what you can do is that, okay, I don't know the network, but that's okay. What I can do is I can generate a proxy network, right? So this is in other words, this is a surrogate network. So just give you an example, right? Let's say this, maybe online service using ResNet 50 to do the image classification, but you don't know that. But here, what you still want to do black box attack is, you say you can using maybe another type of network like VGG network, right? And you using the training data and train this proxy network to generate some of the adversarial examples, right? Because this proxy network is designed by yourself, right? You use the VGG or whatever other network, you have full access to this network architecture and a parameter during this kind of adversarial attack training, right? You can using the training data and generate perturbation to make this VGG network to misclassify, right? You can do this white box attack on this VGG network, okay? And once you generate this kind of attack objects, right? So you generate a bunch of adversarial examples, right? Then you just take these adversarial examples to kind of attack these network, right? So you can using this attack object and feed into this, the network, which is bad blocks, and this can maybe possibly still make this network to fail, okay? But what if we do not know the training data, right? In this case, you still have a solution for that. You can do the query, right? The network give you the outcome, right? So you can upload an image and go through this API. It will generate some label, and then you can form a pair, right? The query image and the corresponding label. You can do this like a multiple queries, maybe 100 or 1,000 queries. Then you get like 100 or 1,000 pairs of training data. Then you using this data to train a proxy network so that you can generate this attack object or images. Then now you can using that to do this kind of attack for this black box network. Okay, so that's one way you can do if you don't have access to the training data, you don't have access to the network either. Okay. So the underlying principle for this black box attack is the learned adversarial example is going to be has some transferability, right? Because you are using proxy network, right, which is the white box model, right? You learn using this proxy network to generate some or learn the adversary that can be very successful, and then you're using this to attack the black box system, right? So the underlying assumption is that there's going to be some transferability of this adversary example. And we are not bounded by just using a single proxy network, right? To further improve the transferability, right? That means, you know, you want to increase the chance, right? The adversarial example you generated can also fool the other, you know, black box system. So in order to increase the transferability, what you can do is you can create a set of proxy network, right? You can have multiple or committee of proxy network, right? For example, you can have, you know, ResNet, you can have VGG network, you can have GoogleNet, you can have different type of architecture of ResNet, different type of architecture of GoogleNet, right? So you can form a set of network, and they all white box model, right? Because you have access to the parameter, and once you have this, you can do this kind of as an ensemble, right? So make sure the adversary example, you know, is able to be very successful fooling this the committee of the networks, right? Let's say you have 10 proxy networks for this ensemble, right? So ideally the objective is you generate some adversary examples so that it can fool all these models, right? And in this case, you can think of the transferability can be improved, right? Because it can make a host of machine learning model to fail, right? And then when you go to using this adversary example, there's a high chance, right? This can also make this black box system fail. So that is, you can using the ensemble method to improve the transferability of the adversary. Okay. So let's look at some of the result from this paper. Okay, so they do this black box attack. Okay, so here this on the, if you look at the column, so this is the proxy network. Okay, let's look at you know, this the first row. Okay, the proxy network is ResNet 152. Okay, and this is the network to be attacked. Okay, so we have 5 different networks, right? ResNet 152, ResNet 101, ResNet 50, VGG 16, and GoogleNet. Okay, so if we look at one by one, right? ResNet 152 to ResNet 152. So essentially, this is a white box attack, right? So the attack model and the proxy model are basically the same, right? So in the proxy training, right, we have access to the models, the parameters, right? So basically, this is a white box attack. So you can see that, you know, under this kind of condition of the setting, the accuracy is 0%, right? Which means this is a very successful attack, right? 100% successful attack, right? The model fail dramatically, right? So become 0% on the you know, accuracy, prediction accuracy. Okay, and then we move on to the next one, right? So the proxy network is 152, and the attack network is 101, right? So it's a different network architecture, but still within the ResNet family, right? And you can see that although it's not 0% anymore, it has some you know, accurate classification, but it's still very low, right? You only have 13% of accuracy, right? We can still consider this is a very successful attack case. Okay. So this is the other case for ResNet, VGG, and GoogleNet. Okay. So if you look at the diagonal of this table, right? So diagonal basically means this is the white box attack, right? So this is the proxy and this is the attack model, right? So they are the same. So have a very high successful rate, right? But the off diagonal is considered black box attack because the proxy network and the target network are different, okay? But still, the accuracy of this network are very low, right? So some of them can be low as, you know, 5% in this case. the author also did this ensemble attack, right? Not just using a single proxy network. So they're using multiple of them. Okay, if we look at this column here, there's a minus sign. That means out of these 5 networks, right, we're gonna remove the ResNet, right, which means the ensemble or the committee of the network they use for the proxy training is, ResNet 101, ResNet 50, VGG 16, and GoogleNet without ResNet 152. Okay. So of course, right? So if you look at the first row, right, if all these networks are considered in the ensemble for as the proxy network to train the adversarial attack, they all have a very high of a 100% successful rate, right? Even ResNet 152 is considered a black box, right? Because it is not considered in the proxy network. You can see still have a 0% accuracy, right? So in this case, this ensemble training make the adversarial transferability improved a lot. And because it has some of the ResNet network in the proxy, and when we deal with the similar type of network, the transferability is going to be very high. This is intuitively makes sense. So this is another case, right? We remove ResNet 101 in the proxy training, and we're using the rest for networks to train the adversarial examples and doing the attack for these different networks. So obviously, if you compare, right, so the result, the numbers here with the table here, the ensemble attack can increase the successful rate a lot, right, by looking at these accuracy numbers here. Okay. So we've talked about this white box attack and the black box attack, right? So the way we do this kind of adversarial example generation is we using this optimization, right, to alter the input, right, to figure out, right, what kind of noise we want to add for one particular input. So in other words, if we have a different input image, we have to do the same process and generate a noise, a perturbation for every input. But then we want to ask, right, is it possible to generate a single perturbation, right? Rather, you have an image, you want to generate the perturbation corresponding to that image. When you have another one, you have to do this again to generate another perturbation. So if you have a set of training data, right, thousands of images, then you have to generate 1,000 copies of the perturbation for individual image. But can we just, generate a single perturbation, right? Using the same perturbation, we add the same perturbation to all the images in the data, and the resulting image is able to be very successful in terms of fooling the machine learning model, right? So in this case, this is called universal adversarial attack, right? Basically, it just means a universal image agnostic perturbation, right? When adding to the natural images, it will cause misclassification for these perturbed image. Okay, so in this paper, they show that this universal adversarial perturbation is possible, right? So we can optimize the procedure and only generate a single perturbation, and with this perturbation, it can be very successful for different images. And we also want to look at some of the examples. We can do adversarial attack in the physical world, right? So before, what we do is we look at the digital world, right? So we have an image, we add in some of the noise or perturbation, and we feed that data to the machine learning model to make the machine learning model to fail the prediction. But how about we do this in the physical world, right? So we actually have to make the perturbation on the actual object, and and also make the machine learning model fail. Okay. So this example we mentioned in the very beginning, right? So we can, manufacture or generate or produce some of the or print some of the patterns on a glass, right? And when people wear this glass, and maybe a face recognition model will fail the prediction, right? So for this person will misclassify or prediction this is this identity, okay? And in the physical world attack, right? So the attacker would need to find perturbation that can generalize beyond a single image, right? Which means this will have some of the property of a universal adversarial attack, right? It's not like if different person, this glass doesn't work, right? You want to, for maybe many people or different people wear this glass, the machine learning model will fail the prediction, right? So in other words, this is going to be more or less like a universal attack. And also is desirable to craft the perturbation that are compromised mostly of colors reproduced by the printer, right? So in the digital world, right? So we adding these noise, but if we want to print something out, right? Maybe print a glass or this pattern or paper, and because the printer, right, the color distortion or the limit, the printout, like the contrast, everything of the printer could create some of the difference as, these perturbation would be in the digital world, right? So we want to have this kind of robustness, right? So once the printout is still going to work. So that's some of the challenges presented in the adversarial attack, physical adversarial attack. And in this paper, they do this physical world attack, and they show that this is also possible and can be very successful. So they're using this stop sign. They print out this poster, and they try the different distance angles, right? When you print out this, maybe put on the window, and you using a cell phone or maybe camera to take an image of this poster, right, with a stop sign, and you feed this image to the machine learning or image classifier, right? And this image, these images will make the machine learning model fail, right? So in their result, their target attack success rate is 100%, right? So you can see this is very successful case, right? We have to generate perturbation and print out this, actual, poster and retake the photo, right? So there's go through a couple of imaging, process, right? So in this case, the perturbation are very robust and also very successful in terms of fooling or failing the machine classification model, machine learning model. And this is another sign, right? The right turn sign and also stop sign. So they also do different kind of perturbation, right? So here maybe just some of the color change, but here they actually crafted some of the graffitis, right? Resemble like the graffitis, right? Have some other special words print out on the sign, right? And this, different arts, print out on the sign. And this may look like a random, right? Like a graffiti, people just write some words on it, but this is actually carefully designed as one type of adversarial attack to make the machine learning model fail to recognize this is a stop sign, okay? And this is another example doing the physical adversarial attack, right? This is to attack the YOLO V2 object detector, okay? So YOLO V2 is a very, YOLO series, a very popular object detector. We can run in real time. People use that a lot. So in this demo video, this is the perturbation or attack example, okay? If this person holding this particular image, right? So some sort of oil painting like, and it will make this YOLO detector failed to detect this is a person. So let's take a look. So as you can see, right, clearly, right, on the left side here, right, the YOLO object detector is able to, very confidently to predict this is a person, right? This bounding box almost show in every frame, right? There's no label switch, right? Very confident to predict this is a person. But if you look at on the right, this person wear this adversarial example here, right? This printout image, and this YOLO is not able to detect this is a person, right? When they flip over, right, without using this example, then is able to make the prediction. Okay, so they actually going to switch over, right? So now, right, this person with this specific design, right, this will make this YOLO V2 object detector to fail to detect this is a person. So you can imagine, right, so this kind of pattern can be easily incorporated, right, like a design of a t-shirt, right? So people can wear, a t-shirt with this type of design, right? People wouldn't notice any difference. Maybe just feel like, okay, this may be a very interesting design or patterns in the t-shirt, but wouldn't think about, okay, this may be some of the adversary example, maybe to fool some of the, detectors, like you go through some of the checkpoint, right? Maybe they are using AI to do person identification or some, person detection, then this kind of pattern can make the system to fail, right? Okay. So we've talked a lot in terms of the attack. So the next we'll talk about defense. So I think we don't have much time. So I think we'll leave the defense for the next lecture. We'll talk about two types of defense, the passive defense and the proactive defense. And we'll introduce some of the method, how we are able to train this machine learning model so that it's going to be very robust to adversarial attack. Okay. So so I think we don't have much time, so we'll end here. We'll pick up this from next lecture. Okay.